So hi everyone, welcome to this lecture. So today we will continue with our previous discussion on graph anomaly detection. So far we have seen, multiple ways to detect anomalous nodes, right? And we have also seen, why anomaly detection is an important problem, and what's the taxonomy. We have seen this figure before, right? So taxonomy of anomaly detection algorithms, right? When it comes to detecting anomalous nodes from from networks. So depending on the networks, the type of networks that these modules are built on, we can classify these models into different categories, right? And we have seen cases where we use static graph, right? Attributed, non-attributed. The attributed case we have seen, we have also seen the pure structural-based approach, community-based approach. In the last lecture, we have discussed how you can detect community and outlier at the same time simultaneously. How one task impacts another task, and so on, right? And we have discussed how we can define anomalous nodes or anomalous structures with respect to a community. And this anomalous structure may not be anomalous with respect to the entire network, but when it comes to a community, then that entity might be treated as an anomalous entity. Okay. So today the plan is as follows. So today we will consider dynamic networks. So, well, there are plenty of methods on anomaly detection for static networks, right? I have only discussed a few, and if you look at the literature review, the survey paper that I mentioned at the beginning in the last class, right? That survey paper is very important. So I strongly suggest you guys to read the survey paper and to understand the state of the art, at least till 2019, 2018, 19 times, and you'll get fair amount of ideas about the methods, right? So I have tried to give you a brief of what people generally consider, right? And two important methods that are often considered as baselines. So now we discuss dynamic graphs. Particularly, we look at the cases where network changes over time, temporal network, and we look at two specific algorithms, right? Again, this space is very crowded. There are plenty of such methods on anomaly detection in dynamic graphs, but I will discuss two important methods that I found to be very interesting, and we also use those methods as baselines in our research. Okay, so what is the problem statement? The problem statement is as follows. You are given a dynamic graph, okay, and this dynamic graph basically changes over time. You have a network snapshot of a network at every time, say at timestamp 1, timestamp 12, timestamp 13, 14, 22, 23, and so on. And you have a snapshot of the network at different timestamps, right? And what's the task? And this graph can be attributed, can be plain, right? And what's the task? The task is to find the timestamps that correspond to a change or event, as well as the top k nodes, edges, and parts of the graphs that contribute most to the changes, right? So we are interested in identifying a particular timestamp or a set of timestamps, right, where the graph structure changes drastically. Okay, now it should not happen that the entire graph structure changes drastically. What would happen is that a few nodes or few edges, right, change their behaviors over time so that they look like anomalous with respect to time. Okay, if you look at the static snapshot of the network at say time t and time t plus delta t, you may not find any abnormality, right? But if you look at the change in the temporal dynamics of the network, right, you see certain abnormality. Okay, so what is the task? The task is to identify the timestamps where this change has happened, right, and the top k nodes, edges, or the part of the graphs which contribute most to the changes. Okay, So, and what are the usual desired properties that we want the algorithms to consider? The algorithm should be scalable. The algorithm should be sensitive to structural and contextual changes, and this is important of change awareness. So basically, we want that the algorithm, should understand that that with respect to which context, right, these changes happen. Okay, we will discuss this further. Right. So if you look at the feature-based approach, so dynamic network, plain feature-based approach. Okay, so meaning that the features are curated manually, right? So what's the intuition? The intuition is that similar graphs probably share certain properties such as degree distribution, diameter, eigenvectors, eigenvalues, etc. So if you look at the snapshots of a graph at time t and time t+1, right, 2 consecutive timestamps, if you see that some of these properties, important properties like degree distribution, diameter, principal eigenvector, these properties change, right, drastically, right? You can say that, okay, there is some abnormality, but in general, right, in general, it doesn't happen. In general, degree distribution always remains powerful. For example, diameter always remains kind of same, right? If you look at the principal eigenvector, right, the components might change, but in general behaves like similarly. It's not that easy to see a drastic change. Now, if you see a drastic change, then it's done, right? But drastic change may not be observed. The reason is very few nodes contribute to the change of the topology, right? It is not that majority of the nodes contribute to the change of the topology. And if this is the case, then you can easily extract, you can easily identify. So what is our approach? A general approach is that you try to extract a good summary for every snapshot of the input graph. So you have a graph at time t, you try to extract a summary of the graph because the graph is very large, right? You try to somehow get the summary of a graph. Now, there are many ways to get the summary of a graph, right? For example, you can just take the, principal eigenvalue, principal eigenvector of the adjacency matrix or whatever, right? You see that how this eigenvector changes over time. An eigenvector kind of gives you an idea of the summary of the graph, right? There are many ways you can also use some sort of stratified sampling and so on, right? Then you compare 2 consecutive graphs. You compare the summaries of the 2 consecutive snapshots of a graph using some distance bit approach. So at t, you have a summary. At t+1, you have another summary, and you look at some sort of you try to look at the dissimilarities or similarities based on some metric. Okay, so when the distance or the dissimilarity is greater than some sort of threshold, right? You can select the threshold automatically or manually. Then you can say that, okay, there is some anomalous behavior, right? So this is the general approach. So if you look at the algorithms that I'm going to discuss, all of these algorithms broadly follow these 3 steps. Okay, so then what are the novelties that these algorithms eventually bring in? These algorithms bring in novelty in terms of how do you summarize the graph, how do you come up with a distance metric to measure the similarities or dissimilarities between summaries of 2 snapshots, right? And the way, how do you define the threshold? Okay, can you define it manually? Defining manual threshold is difficult. Okay, so how do you choose this one? So this is the overall idea how people generally address this problem. People try to use something called maximum common subgraph. There's something called graph edit distance, Hamming distance, right, between the adjacency matrix, right, and some sort of diameter distance and so on and so forth. There are many such proposals, right? So but this one is very interesting. This one was proposed by Lemon Okoglu and Christos Faloustos in 2010, and the idea was to, again, the problem definition is same. A node is anomalous at some time frame if its behavior deviates from its past normal behavior. Okay, So what's the question they are trying to address? They are trying to address the question that at what point of time this changes happen, right? Can we characterize which nodes, change in behavior the most? Okay, these are the questions that we ask, right? So since this is a feature-based approach, they have manually curated 12 features, right? In degree, out degree, right? Outward, etc. But remember, these features are created for every ego net. So what they have done, for every node, they first extracted the ego network, right? The ego network becomes an entity now, right? Now from the ego network, I hope you remember what is ego network. You have the node and the corresponding one-hop neighbors and the connections between one-hop neighbors. So induce subgraph of the node and its one-hop neighbors, right? So then you extract in degree, out degree, total in degree, total out degree of this ego net, right? Out weight, meaning the weight of the out degree edges, right? Outward edges, number of neighbors, number of reciprocal neighbors, number of triangles, etc., etc., minimum weight, maximum weight, and so on. These are all egocentric features. Okay. Now, so what was their idea? Their idea was to see for every node, right? For every node, you have the corresponding ego net, how this ego net changes over time. Okay, because ego net now defines the ego net represents the particular node. Now, if the neighborhood structure of a node changes drastically over time, that means this particular node is anomalous. That is the hypothesis. Okay. Now, so you have 12 features, right? So now think about it. You have different snapshots, right? So every snapshot is associated with an adjacency matrix. So you have, say, let's say you have T timestamps, capital T timestamps, right? You have the capital T timestamps. For every timestamp, you have the adjacency matrix. For every timestamp, you also know the features of the nodes. So I will refer to the feature of the nodes as basically, a feature of the ego net is used to indicate the feature of a node. Okay. So you have different timestamps, T timestamps. You have n nodes at every timestamp. Okay. And okay. So another assumption is that node is set, fixed. Number of nodes is fixed at every timestamp. It just can change. Okay. So I mean, although you can easily generalize it, that's not a problem at all. So T timestamps, you have n number of nodes, and every node is associated with f number of features. F is 12. Okay. So for every timestamp, you can create an adjacency matrix, right? So you have T number of such adjacency matrix. Now we are not considering adjacency matrix here. What we are considering the node cross feature matrix. So you have n number of nodes, you have f number of features, right? And you have some numbers here. So these are numbers, right? We are not considering adjacency matrix, by the way. Because why? Because we are not interested in what is happening outside the ego network. Once the ego network is fixed, now you don't need to look at what is happening outside it, right? So you extract the ego network, you identify f features, and that's it, right? So n cross f matrix for every timestamp, and you have T as such timestamps. So you can think of it as a tensor. A tensor as a 3D matrix, n cross T cross f. Okay. Now what you do, you fix a feature. Let's say your feature is fi. You have 12 features. Let's say you fix a particular feature. Let's say the feature is in degree. We will do the entire analysis on a particular feature, right? And you can repeat the same analysis for the other features. So let's fix the feature fi for the remaining analysis. Okay. So once you have the feature, then you can then this is no longer a tensor. This is basically a matrix, a 2D matrix, right? So once you fix a feature, say in degree or in weight, you have n cross T matrix, right? Now think about it very carefully. Okay, so what is this every entry indicating? So this entry, for example, in let's assume that this matrix is A. Okay, let's assume that. So A I J indicates what? A I J indicates, say A I J equals to say 0.5. It indicates that node J, so and we have already fixed Fi, feature fixed. So node J has feature 0.5, right? Feature value 0.5 at timestamp I, right? So so if you look at the column here, the column is basically the change in feature value of a particular node over time, right? So every column indicates the change in feature value of a node over time. That particular feature value, the one which we have already fixed. Okay. Now, so now what we do? So we can't analyze the this t timestamps together, because t can be infinite. So t can be say 1000, 2000. We can't look at this t timestamps together. What you are interested in looking at, we are interested in looking at the local timestamp, some local temporal interval, say between 0 to 5, then between 1 to 6, then between 2 to 7, then between 3 to 8, and so on. At every local interval, what is happening? At every local interval, what is happening? This is the task. We basically are interested in looking at what is happening within a particular local interval. Okay. Now, so we look at say let's fix this window, right? 0 to 5, 1 to 6. So let's assume that this window size is W. Right? Let's assume that this window size is W. So in this matrix, right, you have n cross T matrix, right? In this matrix, you have one window of size W. You have one window of size W, right? So similarly, this W window, right? This will I mean you can basically slide this W, right? So you have this W, then you move it one step further, move it another step further, and so on and so on. You can easily do that. Okay. So let's now focus on a particular W. Okay. So now your n cross 3 matrix is squeezed into a size of W, width of W. Okay. So basically you have a slice like this in, and this is basically T by W, or sorry, this is W, this is W, and you have T, you have you basically have T minus W time T minus W number of such sliding windows. Okay. Now, right now these are your these are the temporal change of a particular feature of a particular node, right? Now what we do, we measure the correlation. We measure the correlation between features of a pair of nodes within this W, right? We try to understand how similar the nodes are within that particular timestamp. Okay, so we can easily measure this correlation. Pearson correlation, for example, right? This Pearson correlation rho. So you can measure this. Okay. So CXY is the Pearson correlation value, okay, of two nodes X and Y at a particular W, right? So for a particular W, now what you get an n cross n matrix, right, where every entry indicates the correlation between the pair of nodes. Every entry indicates the correlation between a pair of nodes, right, at that particular W time slice. Okay, and you have how many number of such slides possible? There are T, so you have T such time stamps, and the slice is of size W. So you can have T minus W number of such slides, right? Now for every slide, you have this correlation matrix. Okay. Now what does it indicate? This correlation metric at every W, this correlation matrix at every W, it basically indicates the correlation between two nodes, whether they are similar with respect to their ego network structure. Right? Now again, it is difficult to analyze a matrix, right? What we can do, we can essentially get a summary of the matrix, of the correlation matrix, right? So what we do here, we then, you know, slide is not moving. Just a minute. So, right. So, okay. So you have n cross n matrix at every W. Okay. Now what we do, we will not analyze this entire matrix. And remember, this is a correlation matrix, correlation of pairs of nodes, right? What we do, we extract the principal eigenvector. Okay. So at every window, we have a principal eigenvector. So this is the principal eigenvector, right? At time t. I mean, basically here t means a sliding window. Okay. You have sliding window. So at every sliding window, you have this n cross n matrix. From n cross n matrix, you get a vector, which is the principal eigenvector. Okay. This principal eigenvector is basically the summary of the correlation matrix. Okay. So for every t minus W, we have this principal eigenvectors. Okay. Now, so what we have now? Think about it. You have identified the dynamics or the similarities of every node. I would say a signature of every node, right? At a particular sliding window. Now, if you look at two consecutive sliding windows, right? Or forget about two consecutive time windows. If you look at a particular timestamp T or particular sliding window T, right? And its previous sliding windows. You look at the principal eigenvector at sliding window T, and you look at the other principal eigenvectors at the previous sliding windows, right? So what do we need now? You need to compare the principal eigenvector at sliding window T with the previous sliding windows, previous principal eigenvectors. Okay. Now, how do we get the summary of the previous sliding windows, right? So you see here, so say you want to analyze whether this particular time or this particular sliding window is responsible for the anomalous behavior, right? So what you do here, you look at the W or whatever, W minus 1, right? Previous sliding windows. Okay. And you have principal eigenvector at every sliding window, right? So what you can do, you can also think of it as a matrix. Again, once again, a matrix. You can do singular value decomposition, some sort of SVD, or a simplest, the way what you can do, you can look at, you can essentially take the average of all the entries of a particular node. So the first entry in this particular vector corresponds to the feature of that node, correspond to some signature of that node, right, of the first node at this time stamp or at this sliding window. Similarly, if you look at the first entries in other eigenvectors, right, you just aggregate them. Aggregate, you can use average, you can use whatever you want, right? You can also think of it as a matrix. You can do some sort of singular value decomposition. What you get, you will get a squeezed representation of one vector. Now this RT minus 1 is the summary of the temporal change of nodes, right, till t minus 1, right? And what is UT? UT is the principal eigenvector at time t. So you have U, and you have R. Now you need to see the similarity or dissimilarity between these two, right? And this is very simple. Now these are two vectors. These are not matrix, right? They are two vectors. So you just take the dot product. You can use anything. You can use cosine similarity, anything. You can just simply take the dot product, right? This will give the similarity, right? 1 minus this will give you the dissimilarity, and this is captured in Z. Is Z. So 1 minus U transpose R is essentially the dissimilarity of dissimilarity between the eigenvector of at window T and the squeezed eigenvector or the squeezed representation of all the eigenvectors before T. Right? Now, if this number is high, that means there is an anomaly here at timestamp T, because this structure is very, very different from the historical data. I mean, from the previous timestamps. Okay. Now, this is the simple idea. Very simple idea, as you can see. Now, this one what we have done so far. We have fixed a particular feature. We have fixed a particular feature, and we have derived the remaining part. You can repeat the same thing for the other features, right? For the other, for example, this one was done for with respect to feature in weight. You can also do the same thing with respect to other 11 features. Okay, and you get some sort of changes or whatever, similarity, dissimilarity, right? Now, either you think of I mean, there are many ways to handle it, right? Either you think of them as isolated observations, or you can combine them together, create another vector, to do another level of similarity, dissimilarity measurement, and so on. So it is up to you. Okay. So this is the idea. So we have seen how graph summary, I mean, how we can summarize a snapshot, right? How we can measure the similarity or dissimilarity between two snapshots, right? And here we do not need any, of course, we need a threshold, by the way, sorry, we need a threshold here, because this will give you an idea of the dissimilarity. You need to fix a threshold. You say that, okay, if the dissimilarity is above a certain threshold, you can think of it as an anomaly. Okay. So what this method has done, this method has identified the timestamps where you see the change, right? You can also look at the nodes which are responsible for this, because you can easily go back and track which nodes, which eigenvalues, right? Which entries in the eigenvectors are essentially abnormal, right? And you can flag some of them. Okay, so this is the idea. So now we will discuss the next algorithm, which is again on dynamic graphs, but here community based, right? I think you remember the last lecture we discussed how we can detect anomaly and community at the same time from a static network, and we identified anomalous nodes with respect to a particular community, right? But in a attributed network setting. Here we assume that the graph is non-attributed, and the graph is dynamic, changes over time. You have different timestamps, right? Every timestamp you have a snapshot, and then you have the corresponding adjacency matrix, right? What you do, you try to identify the communities, okay, and then you look at how the community structure changes over time. Okay, so you have different timestamps. So here it is not the case that you detect community and outlier at the same time, unlike the previous one. Here we detect community as a pre-processing step, right? Community structure as a pre-processing step, and then we look at how the community structure of a node of a network changes over time, and we try to relate communities across different timestamps. For example, we try to relate, okay, whether community ID I at timestamp T is same as community ID I at corresponding also community ID J at timestamp t+1. Remember, these IDs are arbitrary, right? So we try to basically map. So you have, say, these communities, right, at timestamp t. You have these two communities at timestamp t+1. Now you try to correlate, okay, that okay, is this community emerging from these two communities, or this community gets split? This community, appears because of the split of this community, and so on and so forth. We basically try to look at how a particular community evolves over time, and based on that we detect the anomaly. Okay, so this is a little bit tricky, so just try to focus on this one. Okay, so what's the task here? Monitor graph communities or clusters over time and report an event when there is a structural or contextual change in any of them. Okay, looks at the changes in two subsequent snapshots of the graph or all the snapshots of the graph. Details communities and outlier simultaneously. Okay, now let's see. Okay, so the algorithm that we discussed here is called evolutionary community outliers, right? EC outliers, and this was proposed in 2012 in KDD, right? So what's the idea? The idea is that most of the objects within a community follow similar evolution trends, which is very obvious. If you look at the community, a particular community, and if you look at the objects in a community, it is very obvious because community by definition constitutes nodes of similar types. So by definition, the change of or the evolution of a particular node or evolution of all the nodes in a community should be same, because the nodes are kind of same, right? And we basically try to define something called evolution trend of a community. However, this evolutionary behavior, right, of certain objects is quite different from the average. So what we try to understand now? Now we try to identify that. Let's look at some of the nodes, right? Or say let's look at a community, or let's look at some of the nodes in the community. Okay, and if you see the evolution of the evolution of nodes, most of the nodes or average behavior of nodes in a community versus evolution of a particular node, which is very different from the average behavior of the other nodes in the community, then that might be an anomalous node. Okay, now this is the idea. So let's take an example. Let's say stockbroker, right? So a stockbroker who suddenly changes her portfolio or his portfolio and start investing in another sector against his historical investments, even when other similar stockbrokers continue to invest in the same old sector. You can say that, okay, the first stockbroker seems to be an anomalous entity, right? Because their communities behave in a different manner and he behaves in a different manner. Another example, this was a real example. So let's take example of Tanmoy Chakraborty, who is currently a professor at IIT Bombay. So if you look at his research, right, he started his research in parallel systems, right? His PhD was on computer architecture. Okay, till 1997, he used to publish papers in parallel system conferences and journals. In 1998, he started working on data and information systems, which is very different from this one. If you look at the other researchers who used to work on parallel systems around 1997, 1998, they kept on publishing papers in those venues. But he started showing a different behavior. So he might be treated as an anomalous entity, right? Another example is say in 2010, there are 13 papers in a conference called CIKM on personalization. While none of the other, so CIKM is an IR conference, information retrieval data mining conference, right? So in that conference in 2010, there were 13 papers published on personalized search. Whereas if you look at other similar venues like WWW, WSDM, CIR, ECIR, these are all IR venues. at that year in 2010, right? They they did not publish any paper in personalization. So therefore, these acts as an anomalous entity in this particular network, the conference. Okay. So the community is IR community. There are conferences like CIKM, WSDM, and CIKM acted as an anomalous entity in 2010. Okay. Important point to note is that it is not the case that this a node which is flagged as an anomalous node at a particular time will remain anomalous throughout. This may not be the case. Okay, and this rarely happens essentially, because when he changes his behavior, or the entity changes its behavior, it would look like another entities and the type of entities, and then you can map that entity to that group, right? And with respect to that group, the entity looks like a normal entity. Okay, so now let's look at the algorithm. So what is the task? Again, the task is that at every timestamp we first identify communities. We look at how communities evolved over time, and then accordingly we identify anomalous nodes. Okay, so right, so these are some of the notations that we need to understand. Consider a snapshot series, right? X1, X2, X3, dot, xt. These are t different snapshots of a particular graph. Okay, so we focus on a pair of snapshots x1, x2. So xi plus 1, x1, x2, x2, x3, x3, x4, and so on. So let's assume that this is x1, x2, a pair of snapshots, a pair of consecutive snapshots. Okay, so we denote x1 by a matrix P, but every entry Pij indicates the probability of a node I belonging to a community J. Right? You have snapshot x1, you have x2. So you already identified, so let's assume you already identified the community structure of x1. Now this is x1, you see, and this is x2. And let's say you ran Leuven and you identified these three communities as x1, you identify these two communities and x2. Right? So then at x1 you can create a matrix P, which basically called the belongingness matrix, where every entry Pij indicates the belongingness of a node I to community J. The probability of node I belonging to a community J. Similarly, we have the same belongingness matrix for x2, which is denoted by Q. So try to understand, try to remember the notations. x1, x2, PQ. x1, x2 are two time snapshots, and the corresponding belongingness matrices are P and Q respectively. Now you may say that, okay, how do you measure the belongingness of a node to a community? We'll discuss all these things, right? So what are the possibilities? As I mentioned, if you look at the evolution of a community, how a community can be emerged, how a community can be created. A community can be created because of the split of the previous community, or because of the growth of a previous community. Right? Then let's look at x2. You see a community, you see this community, right? Now this community can be a result of merging of two communities at the previous timestamp, or splitting of a community into multiple communities, or a new community has completely emerged altogether. Right? So we define something called community mismatch. Right? The community mismatch happens due to outliers. So we will not be able to, now if let's say nodes are more or less same. So here there are 5 nodes, here also same 5 nodes are there in this community, right? So these nodes are same. I mean these nodes can be easily linked, right? But if you see that certain nodes are not here, certain nodes which were here at timestamp x1, right? Those nodes are not here in this community, meaning that there is some mismatch. Okay, so let's again look at the notations. We have two snapshots, x1 and x2. Remember, x1, x2 is just an example. We have basically all pairs, x1, x2, x2, x3, whatever, right? we assume that at x1 we have k1 number of communities, at x2 we have k2 number of communities, same number of nodes n, right? We have this belongingness matrix P and Q. P the size is n cross k1, n number of nodes, k number of communities, and each entry indicates the belongingness of node in that community. And you have Q, which is n cross k2, right? So this is P. Each row indicates a node, right? So sum of entries in the row should be 1, meaning a node, the sum of belongingness of a node in all the communities should be 1, because it's a probability ultimately. Okay, so we make sure that the sum should be always 1, each row. Okay, each row should be 1. Similarly for Q, the sum of each row should be 1. Okay, we define another matrix called correspondence matrix S. What is S? S is a K1 cross K2 matrix. What is K1? K1 is a number of communities at X1. K2 is a number of communities at X2. So we basically try to understand the match between one community at X1 and another community at X2. So this is called correspondence matrix, right? So you have communities here. This is K1 number of communities. You have K2 number of communities here, and you have correspondence. Okay, and how do we capture this correspondence? We capture this correspondence using a matrix S, which is K1 plus K2. Okay, S is a correspondence matrix. Remember these notations. Okay, what is A? A is something called outlier matrix. And what's the size? The size is n cross K2. K2 is the number of communities at timestamp whatever, snapshot X2. N is the number of nodes. We want to understand that at timestamp T2 or X2, whatever, right? Whether these nodes are outlier or not with respect to a community at that timestamp. Of course, we'll judge this based on the previous history, but we judge it at particular timestamp T or particular timestamp K2, X2 in this case, right? And every entry AOJ, right, indicates the outlierness score of an object O or of a node O with respect to community J. There are K2 number of communities, n number of nodes, and each entry indicates the outlierness score of the node in that community. Higher the score, higher the outlierness behavior of that node. Okay, X1, X2, K1, K2, PQ, right? Sum of P, each row in the P should be 1. The sum of entries is each row in Q should be 1. You have S matrix, which basically looks at the correspondence, and you have A matrix, which is the outlier matrix. Okay. Now, an object comma community pair. Remember, this is community centric outlier. So we say that okay, now a particular node X, particular node V is outlier with respect to a community C. So you take a pair of object and community. So this pair will be treated as outlier. Okay, if the change in POI and QOJ is quite different from the average change in the community, average change of the community XI to community XJ. What does it mean? So, right, so let's focus on a node O, right? And you already know that P, because P is the belongingness matrix at the previous timestamp, right? You already know how the average behavior of other nodes, right? How the average behavior look like for the other nodes, and how the behavior of this node O, right? And how do you measure this? We look at the correspondence P and Q, and we see how this is shifted, right? And depending upon that, we decide whether this particular pair is a outlier or not. Now let's look at the method. Okay. So what is our task? So what are known, right? So we know this. We know this one. We know this one, right? So let's assume that you have some ways to quantify the belongingness of a node to a community. Already know the snapshot. You can get the community structure. You can easily measure this one. You can also measure this one, right? This is unknown. This is also unknown, right? So your task will be to estimate S, right? What is S? S is the correspondence matrix. Your task is to estimate S such that the distance between Q and P cross S minimizes. Try to understand. So this is P. What is P? P is the belongingness matrix at timestamp X1. What is Q? Q is the belongingness matrix at timestamp X2. What is S? S indicates the correspondence. So the ideal case, if you multiply P with S, you should get Q, because S indicates the transition and P is the initial state. P is the community at timestamp X1. So ideally, this times this will give you Q, but it should not be the case, right? So what we try to do, we try to minimize the distance between Q and P times S. P is known, Q is known, S is unknown, right? So we try to estimate S so that the distance between these will minimize. So the problem here is that this kind of metrics, this kind of approach, may be biased if we take into account outlier. The reason is that when we try to minimize, right, let's assume that we say that, okay, none of them are outlier, right? So therefore, the things would be very easier. You can easily minimize it. You can see the distance is less, then, right? So this is already biased. So then to reduce this biasness, we incorporate something called A. What is A? A is the outlierness matrix. Remember, this is also unknown. So now what is our task? Our task is to measure, our task is to estimate both S and A. Okay. Okay. Now this equation is simple. Let's just try to understand. Okay. So what is our task? Our task is to minimize this quantity. Okay. This is Q. This is one entry of Q, right? OJ, and this is the corresponding entry of P times S. You see, O dot, and so O dot means width row and the entire column. Dot J means jth column, entire row. So you multiply width row and jth column, width row of P and jth column of S, you get the corresponding entry, right? And this is your Q. So you try to minimize this. You take the square loss. Okay. Now, so far we have not considered outlierness score. Now what I'm saying is that, I will not give equal importance. I will not give all the entries of this one equal importance. I would not give all the entries of this one equal importance, right? What I would do, I would give importance of entries based on their outlier score, right? So this is just a weight. You see, this is the entire minimization function, and this is the weight. So let's forget about log, right? So what is this one? 1 by AOJ. AOJ is what? AOJ is outlierness score of object J with respect to, or object O with respect to J, right? We are considering object O and community J, right? So what I'm saying is that if the outlierness score is high, if the outlierness score of a node, of weight node with respect to J is high, this would be low. This would be low. And if this is low, you have less weightage for this object too, right? If the outlierness score is high, sorry, if the outlierness score is low, then one upon this would be high. You give more weightage to those nodes which are not outliers. So now we are trying to shift the bias from more outlierness to less outlierness, right? Okay, and this is log normalized because I want to reduce the impact of the weight. Okay, remember this is unknown, this is unknown, right? So we want to minimize this quantity with respect to S and A, right? What are the constraints? The constraints I've already mentioned. The first constraint is that this S matrix which you want to learn, the entry should be greater than or equal to 0. There should be no negative entry, because what is S? S is the correspondence matrix, K cross K. You see the similarity between one community at x1 to another community at x2. The similarity cannot be negative. So entry should be greater than or equal to 0. The sum of the entries in each row should be 1. Why? Because a community in one, say x1, at x1 you take one community, right? This can be associated with other communities, but the total association should not be more than 1. You are basically trying to get a probability stochastic matrix. The sum of the row of the corresponding matrix should be 1. Okay, and this is another constraint. What I'm saying is that the outlierness score of every object community pair should always be between 0 to 1. Less the score, the nodes are genuine. Higher the score, higher the abnormality. Right? If let's say we ignore the last constraint. Let's say we only take these 3 constraints. What would happen? The problem would be if I say that because remember here, outlier nodes are given less weightage, right? And essentially we're minimizing it. So by default, we'll say that okay, all the nodes are outliers. All the nodes are outliers, right? If all the nodes are outliers, then they will not contribute at all. Automatically this will minimize. Okay, so what the author suggested is that the sum of values of this A matrix, you see, this is sum of all the values of this A matrix. O ranges from 1 to n and J ranges from 1 to K2, because this is n cross K2. Sum of all the entries of A should be less than or equals to mu. What is mu? Mu is a threshold. Mu is a threshold, which basically determines the total outlierness scores of a system. Okay, clear? So this is now this is very straightforward because we have a objective function, right? So this is basically constant optimization problem. You see the constants here, right? And this is not like I mean, these are all constants, and you have this objective function. How we can solve this problem? You can use Lagrange, right? You can use Lagrange multiplier when you then you can basically take all the constraints, move all the constraints to the objective function. Right now, this is your Lagrange multiplier. You see that this beta and gamma, these are your Lagrange multipliers. Right. So you basically move all the constraints to the objective function and subject to these 2 things. All Sij should be greater than or equal to 0, right? Because I moved this one to the here, right? And this one here. The remaining 2 constants are still there. This constant is still there, right? And this constant is still there. 2 constants are there. Okay, and we solve it. How do you solve it? We take gradient descent. Gradient descent with respect to so there are 2 variables, A and S, right? With respect to every entries of A, every entries of S, right? And we and these are the update rules. If you take the derivative, you see these are the update rules, right? And you basically keep on updating things one by one, right? You update until you converge. Now this is the total the overall algorithm. So your task is to estimate S and A, right? So mu is something which is unknown to you. Mu is what? Mu is this is mu, right? This is mu. Mu is the sum of all the entries of A, all the outlierness scores of A, outlierness score of the system, right? This you can either define manually, or here they suggested an automated approach, right? What they suggested is that you initialize mu with 1. Now let's assume that you have only one outlier. Okay, some of this is 1. Okay, then what you do, and then you also initialize Sij and Aoj. Sij can be 1 by K1, Soj can be 1 by Nk2. These are just uniform sampling, right? Uniform assignment. Then you update A and S based on these two equations until convergence, right? Once you get a convergence, then you update mu. Now, what is mu? Try to understand here. So mu essentially is determined by, so let's try to look at this entry. What is this entry? This is the error. This is the noise. This is the dissimilarity. This is the dissimilarity between Q and P times S. Even if after convergence, right, after minimization, we will see some error, some dissimilarity, right? So you see, this is summing over all the entries, right? So this is square dissimilarities between Q and P times S. This is the numerator. What is the denominator? Denominator is the maximum value. Denominator is the maximum value of the entries of Q. Q is the belongingness matrix. Okay, so you basically look at the Q, the maximum value of Q, and with respect to Q, with respect to that maximum value, you see the percentage of whatever fraction of change. Okay, of course this is square, therefore this is square change, and that is your new mu. Okay, you repeat the same step 2 to 6 again, because now your mu has changed. Now once your mu has changed, the other thing will also change, right? Now you stop here when you see that this is kind of remaining, the value of mu remains almost same across timestamp. Okay, this is the idea. So let me recap what we have discussed. So we looked at a pair of timestamps, right? X1, X2. We have two matrices, P and Q. P indicates the belongingness of nodes to K1 communities. Q indicates the belongingness of nodes to K2 communities. We have S matrix indicating the correspondence between community structures across two timestamps. This is unknown. P and Q are known, right? We have another matrix A, which is the outlierness metric, right? And then we define an optimization function. We try to reduce the distance between Q and P times S, right? And we try to get rid of the bias towards outlierness by incorporating this outlierness matrix, right? But it may happen that we end up assigning everyone as outlier. Therefore, we keep a constant of mu, right? Mu will be updated gradually, automatically, right? We will learn Q, we will learn S and A over the iterations, right? Finally, we get this A matrix. We have the outlierness scores of entities, right? And you then take a threshold or whatever. You rank all the nodes based on the outlierness, right? You don't need to take a threshold. You rank outlierness nodes based on the outlierness scores, and then sorry. So here you rank node community pair based on the outlierness score, and then you measure precision at K or recall at K and so on. Okay. Now this is the idea. So this brings us to the end of this chapter, right? If you want to know more about this outlier detection methods, you read the survey paper that I mentioned last day, or you can also read the chapter in the book. Okay, thank you.